Okay, so this is lecture in fact 17, and let me write 17 here, and I'm discussing center of mass. Now, let me tell you what it is. Why do we even want to find center of mass? So let me take this simple object. Wow. It might look symmetric, but it's not really that symmetric like the things written here. Now, if I put my finger somewhere, you see, if I let it go, it will move down like this. So it seems that this is producing a moment around this point, and this moment pulls this down, so it rotates. Moment produces rotation. So it produces rotation, it rotates this way. If I put my finger here, it rotates this way. So there's another moment this way. So I can ask this question, is there a point on this so that when I put my finger, nothing happens? Which means there is no moment of force about this point. And if I can find this point, then that is the point that if I put my finger here, then it is stable. I can just leave it like this and it doesn't rotate. So somehow I have to sum up the moments here should sum up and give me 0. Okay, so, and this point is that center of mass. Now, we will find center of mass, not center of gravity, so I will discuss the moment for mass, in fact. And we will have center of mass. So, let's look at the simplest configuration and see what it means to calculate center of mass, or what is center of mass. So the simplest configuration is if I have like a rod like this, I'm gonna say, and I assume that it is weightless. Yeah, you might say, gee, there is nothing weightless. I know. But or massless, and that's even worse. So, but we can assume that if I put some masses, big masses on this, so we can assume that this is like the x-axis, okay? So it's so tiny, but it is so strong that it can handle some masses, big masses around it. So this is my, say, massless, say, rod or something, and I have some masses here, M1, say M2, maybe M3, say, and maybe something down here, big, so big, and then say. And if this is say point O, a reference point, this one is at distance x1, then this is distance x2, this is distance x3 from O, and x4. Okay, so moment of force is simply this mass times distance from O. If I'm calculating moment of this mass about O. So these are moments about O, right? Moments about point O. So I calculate moments about point O. Now, center of mass will be a point, say here, Cm, center of mass. So that if I say put all these masses together, the sum of all masses here, then it produces the same moment but in opposite direction. So if moments of these masses about O is like this, then this should be say on this side, so it produces a moment of this. So this is produced by this, all 4 masses, this one, this is produced by the four masses, and this one by the center of mass. The masses at Cm. So it's like we gather all of them at Cm. So in a sense, you will see in any course you take in mechanics that you can in fact identify this whole configuration as a mass concentrated at Cm. And what is the mass? The mass is the total mass of this configuration. So you can sum these masses and put it here, and the same dynamics works for that point as it works for the whole, say, configuration. So, and one of them is simply this thing, and the other one, as I said, you will see if you take mechanics, courses in mechanics, then it's like you can concentrate everything at this point and consider the object is simply a point with the whole mass of the object concentrated there. And so we have to sum up the moment due to all these masses and let that be equal to the moment produced by all of them concentrated here. So let's call this XCM. Okay? So if that is XCM, this is what happens. So let me write somewhere here. So moment of all four masses will be, well, first of all, the x's can be positive or negative. This is on the x-axis. So like in this case, this is negative, 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 positive, okay? So that positive, negative is applied. So it's not just x1 times m. The positive and negative apply. So I have sigma on this side, sigma, say I, from 1 to 4 in this case, x, I, mi, right? That is the sum of all moments about O of these masses. And this should be equal to, x Cm times all the masses gathered here. M1, I'm going to write as sigma, times sigma mi. In this case, from 1 to 4, right? So if I put the whole mass, the mass of the system at this point, moment of this should be equal to the sum of all moments, individual moments, okay? And this gives me a formula for XCM. XCM will be the sum of the moments, xi, mi, and let me write, don't write I here, which means I might have more than 4 mi. So for this simple configuration, this is xi mi divided by sigma mi. Okay, so what happens if I have like a solid like a body which is not like this? So what if I have something like this? And you have set point O here. It's very simple. For this one, we also do something like that. So we might, okay, then this I have the center of mass, Cm. Then the center of mass has both x and y. So this is the x coordinate, x Cm, and this is y Cm. And now for x Cm, what I do is I need well, let me draw another picture of this thing. So let's say xcm is here. So this is xcm, this guy here, xcm. Now, it is like I concentrate the whole mass of this object here, then xcm times xcm times the whole mass of the object should equal to x's times dm's. So if this is the dm, say dm, and this is distance from here to here, say this is x, simply x. Okay, so this should equal to the sum of all x dm's, right? So the sum of all x dm's, but the sum of all x dm's is integral, right? So I have integral x dm over this object, say omega, let's call it omega. So it's over this object omega. So xcm will be this integral x dm over m. What is m? M is simply dm. M is simply integral of dm, right? Over omega. Okay? So, and what is, in our case, since we are just assuming the flat objects, we are not considering any, it might have thickness, but the thickness is low and it is constant. So we are assuming that we are finding center of mass for like flat objects. Like I can assume that this is flat. So the center of mass, wherever it is, it means that it is so homogeneous in this direction. So it's the same all the way. But here it's not the same. So what is dm then? What is m or dm? Say dm will be rho dA, right? It is rho dA. It is rho is dA. And what is rho? Rho is mass per area. So that is area, say, what's that? Okay. So that is mass per area, not mass per volume, right? So, and that will be given to you. And in fact, we don't need that. You will see that you have a row here and a row here, and they cancel out, unless that is it changes with x and y. If rho is not a function of x or y or both of them, then we can just ignore it because it cancels out from here and here. Whatever. This is for xcm, and ycm will be something similar. So I have the y dm over dm. Okay, so then now, since you might say, okay, the x and y are telling you this is just single variable mathematics, and we are not dealing with functions of two variables. Yes, and you will see that I will find center of mass for certain, say, regions that I really don't need, say, y here. But anyway, so let's try this. Okay, so what we do is we just at this level we only find center of mass of a region under graph of a function or between two graphs. So this is case 1, which is center of mass of this region omega. So omega is area or region, not area, region under f(x) from to B, on the graph of fx from A to B. So let's find formulas for this one. Okay, so what I said was this is point O, so I have to divide x times dm, and this is dx, and dm is simply, and this is fx on this side, is rho dA, and this is dA. dA is what? Remember, we calculated dA. dA is fx dx. So this is in fact rho times fx dx. So that's the dm. And x of center of mass we usually call x of cm is called x bar, and that is equal to, we had integral over this region, let's write it first, x dm over integral dm over omega. So this gives me a nice formula, omega, since dm is dx times something, so dm eventually has dx in it, so the differential in the end, the eventual differential is simply dx. So the integral should be on x, and x goes from A to B, and we have x, there's a rho, let's write it outside and assume that it is fixed. So if I have x, fx dx here, and the denominator will be rho integral from A to B, that was just dm, fx dx. Well, this one is, you knew it from before, that is in fact area, and this is rho, and then the rho and the rho can cancel out if rho is fixed. So we are assuming that fixed rho, if rho changes with x, then you have to include rho inside. So fixed rho will give me this integral A to B x fx dx over integral fx dx from A to B. Okay. So that is the x of center of mass when rho is fixed. If rho is not fixed and it's a function of x, then you have to enter it, write it inside the integral. Okay, so I will write these formulas at the end again. So let me, so that was x of x bar, say. Now let's find the other one, y bar. For y bar, we do this. We still use this thing. I know if this was like Cal 3 multivariable, then I would just write it the other way. But for y, we do this. We say, okay, this guy here, this dm, what is the center of mass, the y-coordinate of center of mass here? The y-coordinate is simply the middle of this, okay? So this is the y-coordinate of the center of mass of this one, okay, for this dA. So if I multiply this by this, and then the dm is this thing again. So the y-coordinate of this small, let's say that, so this is my differential of mass, right? So remember, I multiplied differential of mass by distance from say y or x, and then sum that up and divide it by total area or total mass, that would give you x or y. Now in this situation, I didn't take say areas like this, or elements like this. I'm taking this element, and this element, the center of this element, so it's like this guy here is concentrated at this point. So my mass, this dm, is concentrated at this point, and this is the y of this, say, element of mass, dm. Now, what is this y? This y is in fact 1/2 fx, right? So my y is 1/2 fx. So ycm, which I call it y bar, is in fact an integral of this guy here, 1/2 of fx times dm over omega divided by omega dm, right? So that is in fact, dm is again rho fx dx, right? So the eventual differential is x. So again, this integral is from a to b. That's what x chain goes from a to b, and I have 1/2 fx. Then this is rho fx times rho fx dx, and the denominator is simply the same thing. I have rho fx dx. Again, if rho is fixed, fixed means that it doesn't change with x or y. So I will get this nice formula. I can get it of the rho, and I have 1/2 integral a to b fx fx squared dx over integral from a to b fx dx. Okay, so that is y bar, and now you will see a much better formula, I guess, in Calc 3 when they discuss these things in 3D. In fact, you can find, there's a formula for z, in fact, z bar. Okay, so that is when I'm finding a center of mass of area under graph of a function. Now, what if I have area and a region between two graphs? So let me erase this. That doesn't hold, so let me, so let me draw this. So I have this one, and the region between these two from A to B. So let's say this is graph of fx, and the other one is graph of gx. Now, oops. So my dm is this. dm is this. dm, this is the dm. And this is x, and this small m is dx. So I just need the dm. So dm will be rho dA, and this is rho. What is dA? dA, remember from the chapter 1, that is simply the top one, which is fx minus gx dx, right? That is the dA. So that is my dm, and let's assume again that rho is fixed. So rho is density, and that I mentioned that is density per area. It's not density per volume, so that's like mass per area. So x bar will be integral over this region of x, which is this thing, x times dm over dm. So this is, again, since at the end I have dx, it is on x, integral is on x, and it is x let's write rho outside, x times fx minus gx dx, and the denominator is simply from a to b, this is the area, and times rho fx minus gx dx. Okay. So that is, when I cancel the rows, I will get a nice formula for that. So this is simple because you could guess that. It's like this one minus this one. So now what happens to y bar? So that was formula for y bar, x bar. Now y bar is, remember y bar was integral of y bar for each one of them. So y bar for each one of them, and this y bar here, this y bar, this thing is from the midpoint here to the x-axis. So this is fx plus gx divided by 2. That's the midpoint formula. Remember midpoint formula? If this is a C and this is D, a midpoint is 1/2 of C plus D, not C minus D. So this is 1/2 of fx plus gx. Okay, so this is this times dm, so that will give me total moment. So 1/2 is over omega, 1/2 of fx plus gx times dm, say, over omega, just dm. Okay. So, again, it is on x, so it is a, b, let's put 1/2 here, and I have fx plus gx times fx minus gx dx, and the denominator is simply integral from a to b, rho, well, there was a rho here, so let's write rho times 1/2. Rho, and the denominator is simply fx minus gx dx. So the top one, that is a plus b times a minus b, and I can simplify that, a plus b times a minus b, and write it in as fx squared minus gx squared. So this will be simply fx squared minus gx squared dx. Okay, so that is center of mass of the y coordinate of center of mass of this object. Okay, so let me write down the formulas that I found. So center of mass, Cm, when I have this situation, fx, y equals fx, center of mass somewhere, wherever that is, it has a x coordinate, x bar, and the y bar. So x bar here is integral from a to b, rho times fx times fx dx, right? Over a to b, rho fx dx. Now, if rho is constant, just eliminate rho. Otherwise, rho might be a function of x. So if rho is not, if rho is a function of x, it is like this. Without that, you can cancel that. So, and the y bar is simply, what did I find? 1/2 integral a to b, and I guess there's a rho here, and I have fx squared dx over integral a to b rho fx dx. Now the denominator is mass, so if mass is given to you, don't calculate it. So if they say this thing has this much mass, then don't calculate mass. Or when you're finding x bar and y bar, I have seen students calculating this twice. Just find it once. Find that area, I mean the mass, in fact, one time, and that's it. So again, here I'm assuming that rho is a function of x, otherwise you can cancel rho. Now the other two formulas are for a region between two curves, and that is this. So let me erase this one and write down the other formulas for you. So if I have a region between two curves, again from A to B, this is y equals fx, and this one is y equals gx. Then I'll eliminate here, then x bar was integral from A to B, let's write rho, and then it was x times fx minus gx dx over mass, which is A to B rho simply fx minus gx times dx. And y bar was a nice formula that was integral from A to B. There was a 1/2 here, and then I have rho here. Then I have rho of x squared minus gx squared dx over the same thing. Rho times fx minus gx dx. And I'm assuming that rho is a function of x. Otherwise, if rho is not a function of x and is fixed, if it is fixed, then cancel it. You might say, what if rho is a function of both x and y? Okay, now you have to wait until count 3. So the worst we can have is rho being a function of x. Okay, so don't go that far. And that can happen. It can happen. You might have some object which has mass. I mean, the rho changes with, say, height, for example, something like human body might be like that. Or height, if you just slice, different slices might have different, say, densities, mass density. So that was the story of x bar and y bar, and see you next time.